Okay, let's get started. It's a pleasure to have Sandipan Roy from University College London, who's going to speak about multiple change point estimation in high-dimensional graphs and graphical models.
Thank you, Richard, and thanks everybody for coming. This is a joint work with Alex Giebert from Imperial College London. So he was previously at UCL as a PhD student, but now he's as a postdoc at Imperial College London. So the talk will be comprising of these things. So I'll start with a brief introduction of graphical models and how the interest among various people in recent times have been in change point estimation in graphical models. I mean, one of the two areas of dynamic graphical models are one where the graph kind of varying smoothly over time, and the other one is like a change point kind of where you have like sharp jumps in the structure. So I'll give a brief introduction or like a brief literature review about those two things. Then I'll go to our model and the estimation and the optimization criterion that we use to find out those multiple change points or estimate. Also, there are some theoretical results along the direction of this high dimensional change point consistency and how those kind of stack up with the classical results. And finally, some application to some financial data and biological data to conclude the talk. So, as we, I mean, right now for the last couple of like 10 to 15 years, there's been an overflow of network data. Networks are kind of probably everywhere. And we are all using some kind of a graph to characterize the networks to model the multivariate dependent structure. And for one simple example would be, one can consider this graph consisting of these four vertices, U, V, W, and X. And the corresponding edges are the ones where the connections are there, like U to W, V to X, and W to X, and they kind of tell you something about how those individuals are connected in the graph or who are the ones connected there. Now, dynamic networks are more common nowadays, or maybe the current technology has enabled to collect those kind of data where the networks are kind of changing over time. So lots of examples are in like social networks, biological networks, neuroscience, and even in finance. Now, one of the crucial things in those dynamic networks is to understand like where the changes or the structural changes occur when the networks are moving over time, and crucial to estimate those time point at which those changes occur. So one motivating example, I will come back to this example in the real application as well. Like for the biology, it's very interesting to understand like if you have like a set of genes like and you use some intervention or treatment, suddenly the gene interaction might change. So what happens to the biologists, they are very interested to know like what those changes signify. For example, in this particular context, we have like a 150 genes which actually correspond to some immune system response in their fruit fly. So it is interesting for them to understand when those changes occur. Like they generally assume like you probably find some changes in those different stages of the life cycle, like embryonic, larva, pupa, and to the final adult state, and whether you can actually recover from the gene expression data those kind of changes at those junctions. It's very crucial for them to understand that aspect. And there are like on the top graph that I have really placed there, there are like two methods that I'm comparing, and I'll come back to them later in the application what those two methods basically signify. But this is just to motivate that time varying networks are interesting in nature, and people are kind of from biology to social science to other disciplines, they are focused in understanding where those structural changes occur. Now, just a brief review of graphical models. So graphical models have now been in for a long time in the stats and computer science literature and in the applied mathematics literature as well. So this basically signifies that I have a set of random variables associated with a vertex set of the graph 1 to p, and I can describe a joint distribution with relation to the graph structure that I have there and the edge structure also. Now, one particular aspect that I must say before, and that I am only considering like the undirected graph here, but there is the other version of the directed graphical model as well. And in particular, the focus would be on like a conditional independent structure in the graph. So basically, where edges would relate to like conditional dependency structure between the variables. So if there is an edge, then those two variables are conditionally dependent given all the others. On other word, vice versa, if they are conditionally independent, there will be no edge there. And one famous book in that regard is the book by Lawrence. So more details can be found there. And so here one key aspect that happens over the when you consider like distribution of a graph structure is that we say that the distribution we can call like have a like a decomposability structure if that can be factorized over G. So basically we can write it in like a product form where Z is typically the normalizing constant and it could have a very ugly form, and calculating it can be sometimes cumbersome, but there are some computational methods both in Bayesian and non-Bayesian where you can actually deal with those kind of normalizing constant. But the key aspect is that here we can find some subgraphs in the, or like some clicks in the graph where over which we can define a computability function like that psi function, and we can write the joint distribution over the entire graph by in some product form of those function psi's. And this would be crucial because when I come back to a particular example of a Gaussian graphical model, you will see that it's one of those graphical models which actually satisfy this structure also, the factorized property. And the other aspect of the graphical model that I would also deal with in my model is the Markov property. So how does the graph encode the dependency structure? So there are typically these two main Markov properties that people are more concerned with. One is like the local Markov property and the other one is the global one. So local one in the sense that any two pair of random variables you take I and j, they are conditionally independent given all the others. If there is no connection between them, or there is no edge between them, I and j. And the global Markov property on the other hand side, if you can find some sort of a set like a S, and you have a set of random variables on A and another set of random variables on B, then X and X will be conditionally independent given X is if such that S separates the A and B in that way. So that basically would tell you that whether you have a local Markov property with respect to the pair of edges or you have a global Markov property with respect to two different sets. Now, Gaussian graphical model is again another example which actually satisfies both these properties. So it's kind of interesting to look at those kind of graphical models in the sense that they have both this local and the global one. So as I was talking about, so one parametric generative model would be, as I was saying, this multivariate normal Gaussian, where this is for the static case that I assume that all of them are coming from one particular multivariate Gaussian normal 0 sigma i.i.d, and that can be factorized over the graph with the H set derived from the precision matrix. So here is a one-to-one correspondence I have because the precision matrix in a multivariate Gaussian kind of encodes all the conditional independent structures. So if any of the entries in that matrix is 0, then that basically means there is no edge, and vice versa. If it is non-zero, there is the edge between them. So one just a brief example would be this particular form where you can obviously see that there are certain entries which are 0 and they don't have edge in that particular graph structure. So that kind of signifies how there is this one-to-one relationship. Now this was very much like an overview of the what like the literature on the graphical models or like Gaussian graphical models have. Now I would move to like more like the pertinent setting that I am looking at here in this particular case is like a dynamic Gaussian graphical model. So many situations, the fact would be we do not realistically expect data to be i.i.d. So rather we are having like network structures change over time, and assuming like identical distribution will basically like blur many of the underlying dynamic mechanisms that is happening. Ages also may be incorrectly classified or interpreted in those kind of context, and also the other aspect there is that no characterization of variance in the age structure because they are changing over time, those ages. So that could be crucial also one needs to take into modeling. Now this particular data set also I would come back, but just I give an example that, for example, I have log return of two different sectors, manufacturing and energy, and even though the marginals kind of look very similar to each other over time, but do we expect like the dependency structure between these asset classes to remain like constant over time? So these kind of questions probably would need like a more like a dynamic graph structure modeling rather than like a static version. Now, typically there are like two different regimes like people have considered. Like one is like smoothly varying graphical models, and the other one that I was saying like where you have like a jumps or change point structure. Now, there may be like variety of ways to relax that identically distributed assumption, but one simplest way to do that is to say that okay, the graph structure is varying smoothly over time. So what that smoothness would reflect into like more like in concrete mathematical terms, like there was a paper in 2010 by some authors, Joe and other collaborators. They showed that the case where sigma z can be used, or sigma z can, if they satisfy this kind of two condition on the first and the second differential, then we can have like a smoothness structure over time. So it's basically saying like your first derivative and the second derivative are kind of uniformly bounded. So that's basically have like a smoothness structure over the graph. But there were later on some other assumptions and some other studies have been done on this area as well. The other aspect that is there is more like a piecewise constant graphical model, or where there is this jump structure. So what if we want to describe those structure, sharp jumps in the graph structure? So one way to say that, okay, let's say I have like this x1 to xp p-dimensional multivariate Gaussian over t time point, such that I want to find out where these changes in the precision matrix happen from t to t minus 1. So this could be like a hard constraint, like a I am putting here more like a non-convex constraint here, that this is equal to k, but this can have like a convex relaxation also for this problem. But one can visualize at least from a top point of view that the change point problem can also be constructed in this way. Now, what are the usual ways to estimate those kind of either the smooth graph structures or those kind of sharp changes? So in case of smooth graph structures, there were like several methods where people use more like this kind of localized estimate, or more like kernel averaging kind of ideas, where they use like a window around a neighborhood of time point and kind of accumulated the observations there to find out like a local estimate of the graph structure of the empirical covariance. But one can clearly see immediately that the smoothness of the estimate will be dictated by the choice of the, or like the width of the smoothing window, like what is your choice of this window width, that would very much affect the smoothness. And the second thing is that being a local estimate, this does not utilize the information outside this window in any way. So that very much like localized in that sense. So that immediately that kind of point tells you that this won't be able to recover the sharp jumps in the graph structure, because this is very much using only the observations within that fixed window. So what would be like an alternative if you have like a sharp jumps, to what kind of estimate one can use? So one general idea would be that, let's say the distribution is coming over t time points from this multivariate normal independent. So I've dropped here the identical assumption, but still, I mean, okay, people would obviously try to tell me that time series independence, that sound not quite right. So, but let's say it's like a basic model at the first, that I just drop the identicalness and assume that, okay, independent over time from normal 0 sigma t. And then I can assume like a strictly stationarity between those change points. So so it's more like a within that window, within a window of like tau k to tau k plus 1, my covariance structure kind of remaining same, and then for another window it changes to another. So like this kind of piecewise structure you can observe. And the goal would be how you can estimate this precision matrix minimizing a convex cost function. So this cost function will have this kind of a structure where you have the likelihood, then you would have like a shrinkage penalty. So shrinkage penalty coming from the fact that I'm assuming a sparse dependency structure. So I'm already assuming that not all of the entries are non-zero. There will be very few non-zero in any particular block, any particular this matrix you consider. Like if there are like k change points, there will be like k precision matrix. So I'm considering for any of the precision matrix I consider, there would be very few non-zero entries. Many of the diagonal entries would be exactly zero. So that basically putting the shrinkage down on those individual theta t's. but then there would be another term that would be like the smoothness penalty. So that kind of stating how your neighbors are kind of similar to each other. It's very much like those fuse lasso kind of idea where you have the lasso penalty and then like this fusing penalty where you have this neighborhood structure kind of smoothing with each other. I mean, there are a lot of work. In the next slides I will immediately show you like.
I think I'm really lost in the notation. XT and YT. XT is your data, right? Now what is XT?
That's like, let's say xt is like a generic variable here that I am minimizing over. So,
And what is XT plus?
so this is like on the positive side. I need to assume that I am on the positive semi-definite cone so that I can optimize over to get that. So that's like the structure. Yeah. So it's just a generic notation. Like it's basically your precision matrix. So sorry for the bad notation. I did. Anyway, so if I go back to more like a specific structure in the case of that kind of multivariate normal, so I can use like a M estimation paradigm where I have this log likelihood term here, then I have the L1 shrinkage and then the smoothness term. Now here there are basically two different versions people can use. So far in the literature actually there are a lot of work on this first one. So shrinkage is fine, people have worked a lot on L1 shrinkage. But in case of the smoothing, there are basically two different directions that people can take. One I have termed here like an independent fusing, one like group fusing. Now why I am saying this independent fusing, because of the L1 norm, this is actually separable. So you can separate out over the ijth entries here, sum over. But when you have like a Frobenius norm, you cannot separate this norm. So that's the more like the group fusing in the case that many of the edges can actually change together, or many of the edges won't change together. So it's basically more like a group structure over the time. So the time here kind of acting, you can think of this index summing over t equal to 2 capital T is like a group. So it's like this group of edges are changing at the same time, or group of edges are changing, not changing at all. So this way, this is more like synchronized in the sense that the edges change simultaneously or not change. Whereas this one is more like where you can sum over all the entries. So here you don't have like this kind of group structure where they are changing together at all. So these are like two different regimes one can use in case of smoothness structure of the graph. Now, definitely this, as I was mentioning, the hard counting constant that previously had, this is like a convex relaxation of that. But nevertheless, these solutions are not too bad to work with this kind of things. And as you can see already that if my lambda 2 is large, I would have a smoother solution. On the other hand, larger lambda 1 would give me a sparser solution. So that generally is the structure of the optimization problem that I'm trying to solve here. And to be more specific in this particular constant, in this particular context, we actually use this second one, the group fusing, rather than the independent one. So to simultaneously, so there was a previous paper by my co-author and some other person on 2017 where they used this kind of estimator to find out the conditional dependent structure, and we in this particular context also use like multivariate observations that are coming from this p-dimensional normal for t equal to 1 to capital T. And remember, we have T precision matrices, but many of them could be equal over time. So we basically have like a block diagonal model space TP cross TP. And this particular estimator, as we termed here, like a GFGL estimator or group fused graphical lasso kind of estimator, we have this loss function and the smoothing penalty, which we want to minimize over the particular set of these positive definite matrices. And the loss function, as I was saying, this one, and the regularizer. So here I have changed from the notation lambda 1 to lambda 2 just for the sake of simplicity in calculation, that I assume that first one is lambda and the second one is kind of a multiple of the lambda, that you can always like do like a scalar transformation in that way. And the change point would be defined as this kind, the cases where the theta t and t minus 1 are defined. And as I was pointing out, you can immediately see that because of this Frobenius norm, this is not separable, and this kind of uh, places you with another challenge in the theoretical setup, because there are methods where you can work with the separable norm, but when the norm is not separable, there are certain ways you have to deal with that. So just to say briefly about, I won't go in much detail on this algorithm part, probably I would spend a bit more time on the theoretical results, but just to say that a typical estimation problem might involve like more than 1 million free parameters, because you can see already I have to assume the H structure, so it's like order of p square. So as your p grows, it's generally growing, so that's why it's become like a more challenging problem. But although the sparsity is there, so you can assume some benefit would be there as well. Now, alternating direction method of multiplication, ADMM is kind of well suited to this kind of problem. So, just to give you like a brief, on the top of the view, like what ADMM basically does, it basically separates the whole problem into two parts. One part is like a likelihood update, which can be solved via eigen decomposition, and that part is basically the most computational part. And the second part is you can update the regularizer via some proximal operator like either soft or group thresholding. So that part is not computationally that involved. This is the first part is the one that places you with this kind of iteration complexity. Now immediately this would make you this would be a big obstacle in using this particular problem to like very high dimensional cases. But even with p equal to 40, you can imagine my number of things to estimate is like 40 choose 2, so which is not small at all. So in that case, you can solve it like roughly under a minute. Depends on how many change points you have basically. But we are personally working on some other, like the computational direction of this problem, that how you can basically have like some kind of sparse eigen decomposition or some those kind of ideas, because I believe that this iteration complexity can be improved. So this is one of the challenges that we are doing now, but for this first work it was more like theoretical, so we did not look at more on the computational aspect of the problem that much. And this is basically the rough view of the algorithm, where you do the so where you have like the empirical covariance matrix, and then you calculate like an eigen decomposition of that matrix, and that eigen decomposition would give you like the update for the likelihood part. On the other hand, you have the other part that coming from the two penalties that you update through some kind of iterative proximal operator. So that uses like a group thresholding or like a soft thresholding. So I'm not going too details into the algorithmic part here, but basically one first part of the problem would take into account like how you can update the likelihood, and the second part would basically iterate over how you can update the two penalty or your the two two penalizer that you have, like the lambda 1 and lambda 2 corresponding to those two small shrinkage penalty and the smoothness penalty. Now, to contrast with previous research that is predominantly, as I was saying, that focused on enforcing smoothness constraints on like age by age level, but here I used more like a penalty that kind of saying like they are changed. So here I have used something that is changing over age by age level, whereas the previous one was more like in a kind of node regression type of context. So they basically use like individual nodes are changing over time. So here it's more like a group of ages are changing over time. And then also this algorithm is a bit modified than the original one they proposed in their earlier paper. And along this direction, in order to reduce the complexity, there were some ideas in this Danaher paper in 2013, where they basically showed that if you have like a p-dimensional problem and p is very large, you can subdivide the problem into like p1, p2, pk, and then solve for each of those sub-problems. So in a way, you can reduce the complexity by dividing the whole problem into sub-dimension. But in this case, I am not quite sure how to do that, but that could be like an idea where people can use this kind of pre-screening to reduce that. And the last one that I was saying previously as well, that many of the active edges may change at the same time, and that changes the graphical structure, and therefore it's more like a synchronized change in the graphical model structure rather than like a node level change. So some empirical result on this direction is that you can even see for the computational cost also, like if you have a, let's say p equal to 40 and you have t like a like p equal to I think p equal to 20 here was, and even like a small case like when t equal to 20 time point, you can obviously see still the group fused graphical lasso computational cost is much smaller than the independent fused one. So independent fused one tends to go off in both the cases whether you keep p fixed or t fixed, and generally in case of the number of change points, so this is the one where probably i.i.d is doing a little better, the independent fused one, than the group fused, that if your change points kind of increased, it kind of still maintain like a similar kind of result, whereas it's probably computational time might increase with in case of the GFGL if your number of change points increase gradually. Whereas there are efficient methods for as I was mentioning in this independent fused graphical lasso case, there are efficient methods for this kind of auxiliary proximity update, which happens to be like T log T. In the case of GFGL, we iteratively project the group norm smoothness constant and these L1 sparsity constant, but here we use like a Dijkstra's kind of iterative proximal update to find out the projection, and that requires like a order of k square t, so that's why probably the k square it is kind of going because of the k square factor here. And even as I was mentioning that for P40 and P100 with approximately like 80,000 parameters, you could still solve it between like 3 to 60 seconds, depends on like how many k you have, so that how many change points you have. So it's not too terrible, but definitely if you want to apply to like really high dimensional problem like P is quite large, you probably need to check that iteration complexity for the eigen decomposition part. And last kind of some results on this empirical part is that in case of dynamic graph recovery, so we kind of use the F-score, which is like this harmonic mean of the precision and recall. Over time, we plotted the F-score for both this independent fused one and the group fused one. And generally, independent fused one tends to do well than the group fused one over like outside the, like as you go a little away from the change point, but around the change point or the vicinity of the change point, GFGL tends to do better than that i.i.d. And the last one is also that typically the independent fused one actually estimate more change points than the GFGL one, so they probably would come up with some of the change points which may not be actually a true change point. So they generally have more false positive than the GFGL case. So that's why with the same kind of F-score, you can see they require more change, or they have like more change points recovered compared to the GFGL.
How about the comparison to the truth?
Yeah, so there are some examples I will show in case of DL data also, where actually true change points are recovered more in the group fused lasso, using the group fuse rather than the independent fuse, because independent fuse tends to select many change points which are not actually presenting the truth. So in one data example, I will show that like later. Now, in case of the theoretical results, so the aim is that I want to limit the error between the estimated change points and the true change point. And also I want to give some idea about the error in estimating the covariance between the blocks so that I can recover the true graph structure. Now, one can view this problem like in two ways. Like either you can say like, okay, because of the k change point, I have like k different block structures, this block diagonal covariance structure. Or from the time steps, you can think of all these covariances are kind of similar up to this time point, and then the change occurs. So there is a way of seeing the same problem in either the block diagonal space or in the time space. So that's like usually in case of the theory, this one basically helps you to visualize the problem when you look at from the block diagonal point. Now, suppose what are the key assumptions we actually need in order to prove some of the results? So these are very some standard assumption that people generally require when they want to prove something about the covariance estimation structure, like the bounded eigenvalues of the true covariance matrix. So the minimum and the maximum eigenvalue are bounded. And the jump sizes, so this is something that comes for typically even in the classical change point literature. So you need a certain separation between your parameters that is changing over time. So if that jump size is too low, that would be problematic for most of the methods to find out the change point or estimate the change point. So you need a sufficient gap between your neighboring covariance matrices. And the third one is like a choice of regularizers. So this is basically comes in most of the penalization methods, that the kind of choices you need for your lambda 1 and lambda 2. And but most occasion in case of the real data analysis, you would either do like a cross validation or like a BIC type idea to find out lambda 1 and lambda 2. And one of the key context here is that we need something like a union of the age set over the all blocks. So this is something I'll come back, that why we need here is basically, so generally when people try to do something like an estimation of a covariance structure, they have a true model space where the true support set. Now in this case, your number of changes are unknown and also the locations are unknown. So you don't know like what is your true model, like what would be your true model set, don't know, because there could be like model misspecifications when you are estimating the true change point. So one way to deal with that, if you consider like a E star, like a union of all the support, like union of the support set of all the edges or all the block diagonal covariance matrices, that would basically help you in that sense, that when you have to deal with this potential model misspecification of those change points. Now, under those key assumptions, if you have this kind of a jump size, so this is probably, these constants are, I don't think that these constants are optimal, I think these can be improved. So anyway, but to look at the rate, like this is kind of the jump size rate you require in order to say that something on the maximum error that you encountered for estimating the change point, or the maximum error that can be bounded with high probability. And in order to see like what is the kind of rate that you're getting for the change point estimate here, so typically what people do, that they divide by the t both sides to look at like a ratio. So let's say if I divide here like delta t, then delta t is roughly coming like a square log k plus beta log p by t. Now, in classical change point estimation, the rate is generally like typically the rate in case of the classical change point is order of 1 over t. What you are getting in this case, if you see that you are having, so if you take the t on this side, you are getting a t here, which is here, but you have a log factor on the top also. Now, I don't know whether this log factor is the optimal one, but which is something you don't totally unexpect also, because of the high dimensionality problem, you would probably have a sparsity factor and also like beta log p over t. Now, log k probably grow much smaller than t, that is fine, but you probably still have a high dimensional factor that is coming from this beta log p term, and beta is something like a constant that you can see here is greater than 2 here. So that's I'm completely unsure whether this is the optimal rate in the high dimensional multiple change point estimation, but this is something that you can actually compare with what you get in the classical literature also. At least up to the log factor on the top. Now, just to give a little bit idea about the kind of the roadmap for the proof, like as I was mentioning, that we use the set epsilon star as the support, or E star as the support set, opposed to the true graph structure for each block case, since you do not know a priori where the blocks start and begin. So in order to help with that model misspecification or potential model misspecification in change points, we use this kind of union support set. Now, key equation is the stationarity condition that you get from the likelihood. So this is your, if you take the if you look at the first derivative of that term, then you have this subdifferential for the lambdas, the smoothing and the shrinkage penalty, and here you have the likelihood, that is the derivative coming from the likelihood part. Now some algebraic calculation using like the stationarity condition for the 2 points like tau hat k and tau k, and then if you take the difference, then that would yield basically these two terms here. So if you look at the second term basically is like a empirical covariance minus the true covariance. So this is pretty much like a sampling error kind of term, and the estimation error kind of term that comes in the first term or in the first term. So these are the two terms that you need to control in order to get a appropriate bound for the tau hat k minus tau k. So one term involves like an estimation error, second term involves like a sampling error, which involves the empirical covariance minus the true. And this kind of similar term actually came in the case of a paper by Ravi Kumar in 2008 also, but the fact is that they dealt with a one stationary, like a one block structure. There were not multiple blocks, there were one covariance matrix they are trying to estimate. So you can think of like a stationary case there, but this kind of sampling error term appeared even there also, and we use some of the ideas from there, but we have to a bit careful here because we have like a k multiple blocks here, and also like a potential model misspecification because we don't know the location of the change point. And the other bound, the concentration bound, that also can be or can be adopted using some of the ideas from that paper, but we need to use those in the case of multiple blocks, and we have to take care of the fact that there are potential misspecification of the change point positions are there when you are doing that. And these actually because we don't know where those potential misspecification occur, that's what's kind of the motivation behind using this kind of union of k graphs, like union of the support set, that kind of helps you to deal with the true model space and the complementary model space. And using the above two bounds and the stationarity condition, we can show that this maximum is tied with high probability. So that was the kind of reason. Now in comparison with, so there was a work in 2012 where they used this kind of similar penalty, like this kind of L2 Frobenius norm penalty. But what Kohler and Zink did, they actually look at like a neighborhood type regression. Instead of a global graph structure change, they looked at like a individual node wise regression where the nodes are changing on the influence of the other nodes. Now the other also there is another separation also there because they did not consider, I think, the high dimensional structure there. So there were more like the standard dimensional asymptotics there. Although the change points were allowed to grow, but not the dimension there. And the fact is that what they did, so if you look at the bound they kind of obtained here, was this is the kind of bound they obtained at the column or row wise level because they were doing like a neighborhood type regression. This is like a very naive calculation, but what I am trying to motivate here, that if you have like a neighborhood regression and if you combine all the structures, it may not always reflect your global change. That could be erroneous, that when you are combining the neighborhood type regression. So there is a difference between looking at like a change. I mean, obviously there is a motivational difference. First of all, like some examples might require you to look at like a global change rather than like a node-wise change. Secondly, if you even look at like a node-wise change and try to reconcile them or combine them, there might be, that combination might be erroneous. So there could be error encountered when you are combining those individual node-wise regression estimates. Now you can see like if I combine the jumps across the nodes, I can see that so this is very naive calculation. I mean, this may not be too concrete, but just to show that there could be settings where if P is large, where you probably say this jump size is much larger compared to my even if I compare across different nodes. So to kind of find out or recover like similar change points, you probably may not be able to do or find out those change points using like a combination of nodes or combination of the jumps across nodes rather than using like a one global jump for all the different matrices. And lastly, as a byproduct, you also get like a Frobenius now error consistency under those assumption and the sample size requirement on T, that with high probability you can also bound the maximum of the difference between the estimated theta and the true theta in the Frobenius norm. So that's kind of a byproduct of the result, because when you are trying to find out this thing, you anyway have to prove this, like to control these things. So that kind of comes as a factor of controlling the change point. Now, just to finish up with some application that, so this is a monthly log return from 1925 to 2013, like T is really large. I mean, this is probably not the ideal example of high dimension, but anyway, like P, there are like 7 industries, and I have like lambda 1.2, and I fix my shrinkage parameter and vary my smoothness parameter over independent fusing and group fusing. And the point I was mentioning that this IFGL tends to find out a lot of the change points, and so here in this case we have been able to like find out like where people have studied this data and find out saying like what are the true change points in this case, and it seems like the GFGL kind of correspond to those years more accurately, or find out those years which actually the change happened, rather than these spurious changes they find out in the IFGL. So some of these may not actually make any sense. So this is basically the case of IFGL, that they tend to select many of the change points which may not actually exist, whereas group fused graphical lasso in some sense, I mean, which I'm not saying that or preaching that you always use group fused graphical lasso, but for certain examples it probably makes sense to use like a synchronized change rather than individual node changes, which IFGL kind of propagates. So in some sense you'd probably be more better off saying like how, if a group of edges changes together rather than one particular node changing over time. And last example was like a dynamic gene dependency network. So we have like a 150 genes that relate to like immune system development, and I have like 67 time points over the life cycle of this. So here definitely I am in a very high dimensional setup. You can obviously see I have to find out like order of p squared type age entries, and I only have 67 time points. And it is interesting for the, as I was mentioning, for biologists to understand why or how like regulation of gene activity after some interventional treatment evolves over time or changes over time. So we use like both these methods, IFGL and GFGL, but you can obviously see the group fused graphical lasso changes are sharper than IFGL. So IFGL is kind of more smooth over time. So GFGL on that case sharply identify where those changes basically occur. So that way it's correspond to what the biologists kind of thought, that where those changes would basically appear. Whereas this one is pretty much smooth, and they also tend to, as it happens in case of IFGL graph structure also, they kind of recover a lot of the entries which may not be were there in case of over time. And finally, we can utilize to other financial setting also for the construction of the index portfolios, or like a worldwide map of like dynamic asset dependency if we have that kind of global structural data. And in case of neuroscience, actually people have already started in fact for inferring like a connectome structure, so which is a very hot area I think in neuroscience, that where people are trying to find out this kind of graph structures or brain structure changing over time for multiple individuals, or even like over multiple time points, and then prediction for second order, like if fMRI activity, can we predict how the brain responds to like different tasks? So that is also very crucial to understand, like when you are placed with some different physiological tasks to a group of individuals. And algorithmically, how we can make like this thing more useful for larger data sets. So that is one of the challenges still remain, like because that complexity is like order of PQ, as I was saying. So that's still one of the challenges that we are facing, that how we can make this thing more useful for larger data sets. So that's like a computational aspect. And as just to summarize that, I presented this kind of consistency of multiple change point estimation along with the recovery of the graph structure in this high dimensional time series of graphs. but graph-wise smoothness constraints kind of enables how you can characterize like many edges together changing over time or kind of remaining same. And obviously these ADMM type of algorithm are efficient in this kind of particular convex and linear composition properties of the GFGL enable that to do that. But still one of the challenges that remain is how to make this more scalable with large data sets. And many applications in finance, gene interaction, inferring like connectome structure, which is probably another area that we are looking like how we can employ it to like brain structure estimation problems. And an early draft is there in that, but maybe a little more updated, but because some of the results I presented, they're a little more polished form, which may not be exactly there here. So that updated one should be up in the archive in a couple of weeks' time. And early prototype for a package is also available in this website where you can play with this algorithm, or if you want to see like how you can make it more scalable, feel free to do that. And the review of this thing is also appeared in other journal where Alex worked with another person. I'm the same person whom we worked with before to look at about this kind of group-fused graphical lasso problem. Thank you very much.
Questions for Sandipan?
Then I have a question. This is very nice result. I also work on similar stuff, so I know how hard the computation part is.
Yeah,
So
yeah.
I think it's really good that using this method can deal with this data
Yeah.
in such faster algorithm. It's about your that rate. So can you go back to that rate? I remember you have a S squared there.
Yeah.
So So I think it's the S squared make it not optimal.
Yeah.
Because S squared, if you just look at one single graph, not to talk about this dynamic stuff, S can be as large as all the square root of n over log p. If you plug that in here, then it's not optimal.
Yeah.
And also from another, you deal with just S equals 1, but I mean,
Yeah.
everything S equals 1, but you merge everything together.
Yeah, I agree with you because I am using that union structure. So S is actually quite large here.
Yeah.
So that's actually making it a much loose than what we generally expect it to be.
Exactly.
Yeah.
So that relates to my next question. It's also for the S definition.
Yeah.
Why is it necessary to define S in this way instead of just like every 2 pair? Because every time you apply your penalty only on a pair, right? So, well, I don't know, of course.
Yeah, I mean, this is probably also due to the proof strategy. Like, so they, in the case we tried to see like the kind of approach people did earlier for stationary or one block case. So they were using like a primal dual approach. So they solved the problem for like a restricted version which belongs to like a model subspace. And then you show that if the restricted version satisfies the one that is outside the model subspace is very small in error. So that way you can actually control the whole error in the estimation. But what happening here in this case that model subspace is the one that is problematic here because you don't know a priori where the block starts and where the block ends. So if you probably, when you are estimating, you probably end up in a potential model misspecification case. So if you consider like a union, you probably would never be kind of going away from like a true model space. You would probably end up always there. So that's like the.
Yeah.
I agree that what you were saying that direction could be something that can be thought of, but I did not have much idea like how to proceed with that kind of support set. So I thought that, I know this is very probably naive way of taking like union of all the support set, and that probably is one of the reason why this A star is huge. This S is huge, so that probably makes the bound not optimal. But at this point, I cannot think of. I personally worked on a single change point case myself in like similar kind of setup. And in the single change point case, actually, we did not come up with this thing. because we don't have, because single change point case, it's much easier the model misspecification, because you know that either you are here or you are here. So if it is your true change point, you are either left or on the right. But in case of this kind of multiple change point, there could be mismatch in both the direction, right? Either on the right side or on the left side on your interval. So it's much more complicated to deal with that model misspecification. I mean, I feel like I don't have much idea like how to maybe do the direction that you were saying, like, which I agree that probably would give maybe a better bound on this. Yeah.
Thanks very much.
Thank you.